Question 7 is a chromatography experiment where we are preparing 100 milliliters of a 0.340 moles per liter sodium chloride aqueous to use as our solvent. Calculate the mass of solid sodium chloride needed to prepare 100 milliliters of the 0.340 moles per liter solution. So again, this is a unit conversion, and I like to do these questions by doing a conversion chart. So remember that we can express the quantity we have in mass, we can express the quantity we have in moles, and because this is a solution, we can also express the quantity we have in concentration, which is also known as molarity. Now, to convert between each of these variables, I like to use the equations. So to go from mass to moles, we use N equals M over M. And then to go from moles to concentration, I use C equals N over V. So I'm actually given the concentration in this question, and I'm being asked to find the mass of the salt that I use to dissolve in that 100 milliliters. So I need to go from concentration to moles first, and then from moles to mass. And so it's a kind of a two-step unit conversion. So let's change concentration to mole by rearranging this equation. Moles is C times V. So the moles of salt or sodium chloride is going to be 0.340 moles per liter times 0.100 liters. Okay, that's 100 milliliters, but we need to make sure the units cancel out properly. And that gives me a mole value of 0.034 moles. Now I'm going to change the moles to mass by rearranging this formula. So, and the molar mass, by the way, is capital M, and that's given to me in this question. So the mass equals N times M, 0.034 mole times 58.44 grams per mole. Moles cancels out, and we will get a final mass value rounded to 3 significant digits because this value, this concentration, has 3 sig digs, and so our final answer should reflect the lowest significant digits that I have or that I'm given, and so I'll round this to 1.99 grams. So what this means is I dissolved 1.99 grams of NaCl dissolved in 100 milliliters of water to create the concentration that was given to me. All right. So question B is asking me to use the materials in the data table in my materials list to explain how I actually would do this in a lab setting. So it says here that not all the materials actually in the list may be needed. So we'll just think about this carefully. I will need the solid sodium chloride for sure. I will need a balance to measure out the 1.99 grams. Do I need a pipette? Probably not, just because I don't really need that to make the solution of salt. I will need distilled water. I definitely will need a 100 milliliter volumetric flask because you remember that a volumetric flask is actually more calibrated, more accurate, even than a graduated cylinder. And having 50 milliliters graduated cylinder, that wouldn't be so useful because I would have to do this twice, measure it twice, and it would not be as accurate as this guy over here. Same thing with the beakers. I don't think I really need that just because we don't use beakers to measure volume. A weighing paper and scoop, yes, we definitely need that because we need to weigh out the salt and then we need to scoop it out as well. So step 1, using the weighing paper and scoop, okay, perfect. Measure the correct mass of sodium chloride on a balance, great. After you have that, what we have to do is we need to mix the sodium chloride with water, and we're going to mix it in this volumetric flask here, okay? So we're going to say here, and again, you can look at the AP answer key to see their exact wording, but I'm just going to paraphrase it. We are going to combine or mix the 1.99 grams of salt with distilled water. Now we should use 100 milliliters of it, obviously. So we're going to mix it with 100 milliliters of distilled water. In the volumetric flask. And we'll be specific. So we'll use in the 100.0 milliliter volumetric flask. don't know why this keeps erasing there by itself. All right, after we do that, it says here we're going to swirl the mixture to dissolve the solid sodium chloride. And so what we're going to do in step 4, there's an extra blank. We need to just be accurate with our volume of water if we want to make this very accurate of a concentration. So what we typically do after you mix is you check the calibration line. So a volumetric flask looks like this. It's kind of like a bulb at the bottom, very round at the bottom. And then there's a line. So that line is calibrated to exactly 100.0 milliliters, okay? So in step 2, if you didn't get it exact, we're going to double check and make sure we are exactly at 100 milliliters. Actually, maybe I can leave this drawing here. We're going to double check and make sure it's exactly at 100.0 milliliters. So it's properly accurate and we fill it up to that calibration point. So we're going to top up the volumetric flask with distilled water. I guess maybe we could use a pipette here to just do it by drops if we're very close, but I don't see that on their answer key. So we'll just top up the volumetric flask with distilled water up to the 100.0 milliliter calibration line. And then finally, we're going to stopper and invert the mixture, mix it several times to make sure it's homogeneous, and that's how we prepare our solution. The final question here says the student uses sodium chloride solvent to separate a mixture of compounds X and Y in a chromatography experiment. So these are probably ions, I'm guessing. So because sodium chloride is ionic, I'm assuming X and Y are also ions. So after 30 minutes, the student removes the chromatography paper from the chamber or from a beaker, and the results are shown here. So we see that compound X has traveled up a distance and compound Y has migrated even further. And the solvent front, as you know from chromatography, is near the edge of the chromatography paper. Okay, so what does this question say? It says that a second student conducts the same chromatography experiment but removes the paper from the chamber after 15 minutes instead of 30 minutes. Predict the effect, if any, this would have on the separation distance between compounds X and Y in the new experiment and explain why. I would think that the separation of these pigments would be they wouldn't travel as far simply because they were not in the aqueous solution for long enough. So what effect would this have? Well, I think that the X and Y would travel a smaller distance. And that is because of the reduced time. Because also the solvent front will also not travel as far in that reduced time. So the solvent front will also not move as far, which will actually contribute to these pigments, or I mean, they're not necessarily pigments, they could be ions, resulting in them not moving as far. So the solvent front will also not move as far due to the decreased time. All right, that concludes this question.